Hi everyone, my name is Maxim Sharabayko. I am Senior Software Developer at Hivision, SRT Research and Development Team. On behalf of Hivision and SK Telecom, I would like to make an overview of the Secure Reliable Transport Protocol. SRT is a protocol built on top of UDP. It is content agnostic. It provides bidirectional data transmission with automatic repeat requests, forward error correction, and bonded connections. It also supports stream multiplexing so that several connections can be established over a single UDP socket. The major purpose and use case of SRT is low latency live video contribution and distribution over unreliable networks. I will talk about that in a minute. In this presentation, I will first go through the main concepts and technical features of SRT. Then I will share some ideas and thoughts on why SRT and why IETF. Let me start with a short overview of SRT packets. The core of any protocol is how the communication is being performed, what kind of packets are used. SRT packets are transmitted in the payload of UDP datagrams. This slide shows the placement of SRT packets in a common packet structure. Every SRT packet has its own header and packet contents. There are two types of packets in SRT: control packets and data packets. Packet type can be distinguished by the corresponding bit flag F. Control packets are used to interchange control data, which includes handshake, acknowledgement, negative acknowledgement packets, and other. Data packets are used to transmit the actual payload of forward error correction packets. Using control and data packets, SRT offers several operation modes: message mode, live mode, and buffer mode. Message mode can be used to transmit messages that span over several packets. Live mode is a subset of message mode with additional features to enable real-time live stream transmission with a constant end-to-end latency and possibility to drop too late data. Finally, the buffer mode is used to open a connection, transmit a single and large piece of data, and then close the connection. The major purpose and use case of SRT is low latency live video contribution and distribution. The corresponding operation mode of SRT is called live mode. The live mode provides a fixed end-to-end latency that includes network transmission latency and a configurable buffer and delay of the receiver to recover packet losses. The receiver delivers the data packet to an upstream application not earlier than after the specified latency has expired. Live mode provides an additional benefit of recovering the timing of the source VBR streaming that can be distorted by network transmission. This recovery of timing helps decoders and playback devices to add only minimal additional latency for decoding, while the whole management of the end-to-end latency is performed by SRT, so that application doesn't need to implement and handle it itself. SRT preserves the end-to-end latency because it knows the timing. Every SRT packet has a timestamp indicating the relative time when this very packet was submitted to SRT on the sending side. This slide illustrates the retransmission of the third packet that happens within the predefined end-to-end latency value. Based on the packet timestamp, SRT receiver knows the time this packet is to be delivered to an upstream application. The receiver keeps the packet in its buffer until the delivery time has come. This mechanism is called timestamp-based packet delivery, or TSBPD. Based on the timestamp, receiver can try to recover a missing packet up until the delivery time of the next data packet. If a lost data packet is not recovered, but the time to deliver the next data packet has come, the receiver will drop the missing packet to preserve the end-to-end latency. For example, in this case, the retransmission of the third packet fails within the predefined latency, so the packet will be dropped. Dropping a packet means the packet is considered lost. No further attempts to recover it are made, and the following packets are being delivered. This mechanism of dropping a data packet is called too late packet drop, or TL packet drop. I would like to highlight at this point that even in live mode, SRT remains content agnostic. It doesn't know the payload it transfers. All operations are based on SRT headers exclusively. Examples from previous slides illustrated the recovery of lost packets with automatic repeat request mechanism, that is, letting the sender know there was a packet loss and expecting it to be retransmitted. This is done in SRT by negative acknowledgement packets receiver sends back to sender. These packets are sent once a packet loss was detected, and periodically to let the sender know an updated state of the receiver. Each NAC packet can hold several sequence numbers of lost packets and even ranges of sequence numbers. Besides ARQ, there are other possible packet recovery options like forward error correction and bonded SRT connection. In case of forward error correction, SRT provides an extension and certain packet formats to apply any custom forward error correction algorithm. In case of connection bonding, several SRT connections can form a single bonded connection. Thus, a certain type of redundancy can be utilized to increase the chances to deliver a packet, or at least increase link throughput. 3 bonding modes will be supported in the upcoming version 1.5: broadcast, main backup, and load balancing. I will not go deeper into this due to time limitations. Besides notifying a sender about lost packets, SRT also uses regular acknowledgement packets to acknowledge the reception of a certain sequential number of packets. ACK packets have a dedicated field called last acknowledged packet sequence number +1. Acknowledgement packets are sent periodically, by default every 10 milliseconds. They also carry some useful information estimated by the receiver like RTT and link capacity. For high data rates, receivers should send acknowledgements more often. In that case, a lighter acknowledgement packet is sent on every 64 data packets received. Light acknowledgement carries only the last acknowledged packet sequence number to reduce the overhead. Positive and negative acknowledgement mechanisms can be utilized by various congestion control algorithms like the well-known and widely used cubic and BBR. Which congestion control algorithm to use is the decision of the implementation. In a non-live streaming mode, the existing SRT library uses a variation of the additive increase, multiplicative decrease algorithm, relying on link capacity estimation and loss reports. Live streaming is a special case of congestion control because the maximum sending rate is limited by the bitrate of the source streaming. Congestion control should do all the best to preserve the source streaming rate, while the pacing and retransmission decisions can be adjusted by congestion control. Also, sender may decide to prematurely drop some packets to reduce network congestion. That is roughly what live congestion control in the existing SRT implementation does. There is a lot of room here for smart decisions. SRT manages connections based on the dedicated SRT socket ID field present in every packet. For example, data packet and a handshake packet are shown on this slide. By means of this SRT socket ID field, SRT provides a bidirectional data transmission and stream multiplexing, making several connections on a single UDP link possible. SRT establishes a bidirectional connection after a handshake. There are two types of handshakes. The caller listener handshake is used to establish a connection with a known server that has its UDP port open. In this case, caller initiates a connection by sending an induction handshake. This type of handshake is on the left. There are use cases when there is no possibility or it is ineligible to change firewall configuration and open certain ports. SRT offers a special rendezvous handshake procedure when both parties send a wavehand handshake to each other and decide who is to be a caller. These outbound handshake packets traverse the firewall to allow incoming UDP packets from the peer. In both cases, SRT connection establishment takes about 2 round trips. String configuration is exchanged in the handshake, including latency negotiation, encryption configuration, and so on. A notable feature here is that an additional user-defined data can be provided in the stream ID field. The stream ID field of the handshake packet holds up to 512 characters of custom user data. The content is not restricted by SRT, but SRT also provides the so-called SRT Access Control guidelines that suggest a format to exchange some useful information like username, requested resource ID, stream content definition, and so on. For example, based on the username extracted from this field, a server can find a matching passphrase and let SRT compare it to the one provided by the peer, thus allowing multiple users to connect on the same UDP port, but each having its own passphrase. This takes us to the next feature of SRT, encryption. SRT offers IS encryption of the payload of data packets. The payload is encrypted with a cipher in counter mode. The counter mode is suitable for continuous stream encryption that permits a random access decryption of more or less any packet, and thus tolerates packet losses that are allowed to happen in live mode. Therefore, when a data packet is lost, the decryption of further packets doesn't suffer. Packet sequence number and message number are used to derive a counter value for each data packet. Unlike the payload, headers of SRT packets are not encrypted. This allows processing of packets without knowing the encryption key and without getting access to the payload. A pre-shared password is used with a password-based key derivation mechanism to establish an encrypted connection. Potentially some other automated key distribution methods that scale better could be proposed as well in the future. The encryption workflow is a separate topic that requires a separate presentation. For more information, please refer to the SRT protocol technical overview. I just would like to make a note that SRT can potentially be extended with other encryption and key exchange mechanisms. So why SRT? SRT is not an attempt to reinvent the wheel. SRT, in a way, is the wheel. It was created and first used in 2013. In 2017, SRT was made open source and free for public usage. At the moment, SRT has been widely adopted and has become a de facto industry standard for live contribution and distribution. Companies using SRT are joining the SRT Alliance that currently counts more than 350 members. Only last year, more than 100 new companies had joined SRT Alliance. It is a good indicator that SRT is a highly demanded solution of a still topical problem of live contribution and distribution. SRT is very flexible, multi-purpose and content agnostic. Its open source implementation is very easy to use because it provides APIs similar to UDP and TCP socket APIs. The library is backward compatible, so that the latest version still supports previous versions of the library. Now, why IETF? Up until today, SRT is still an implementation-driven protocol, but it is about time to provide an official specification for the protocol so that anyone can use it to write an independent implementation and be sure to be compliant with the world. That is one of the reasons for SRT to be presented to IETF. Another motivation is to become a part of a great IETF community, to get a valuable feedback and experience and continue improving the protocol. Thank you for your time.